Welcome. This project is on deep learning of human brain activation. In this project, we will look into ways to create better diagnostic tools for neurodegenerative diseases such as Alzheimer's disease and non-cognitive impairment. In recent years, deep learning, the idea of designing and training deep neural networks to perform tasks, has been very popular, and we will too be using neural networks to create a classifier that can differentiate between patients with Alzheimer's disease, patients with non-cognitive impairment, and cognitively normal people. The brain is made up of billions of neurons. Given such complexity, we still do not have a complete understanding of our brain. For example, we do know the process of aging is due to the formation of abnormal lysosomes. However, neurodegenerative diseases take on a different path. When abnormal groups of proteins form in the brain, they cause cognitive impairment by damaging and destroying neurons in the brain. Dementia happens when mental processes are affected by neurodegeneration. A large majority of dementia cases are due to Alzheimer's disease. From now on, we will call Alzheimer's disease AD. The process of neurodegeneration, dementia, can be seen as a 5-stage process. Starting from a cognitively normal person, the early stages of someone with AD will see him having early stage mild cognitive impairment. We will call mild cognitive impairment MCI for now. If left undiagnosed, it will gradually turn into MCI, and then late stage MCI. If left untreated, it will deteriorate into AD, and by this time, the person will have significant memory loss, behavioral changes, inability to learn, and eventually organ dysfunction. If you look into a brain of someone with AD, it will look shrunken and wrinkled. AD is increasingly prevalent in our current day and age, given our aging population globally. According to Alzheimer's Disease International, one person will develop AD every 3 seconds. 4.8 million people worldwide are living with dementia in 2015. This number will almost double every 20 years. Yet, not only do we lack a cure, scientists do not fully understand the mechanism behind the disease. This makes early detection our best hope currently. World Alzheimer's Report 2011 shows that early diagnosis and intervention is an important mechanism to close the treatment gap. However, more effort has to be done to improve our diagnosis process of AD. Thus, there are 2 main objectives of this study. First, we want to identify biomarkers of AD and MCI. Second, we want to come up with a methodology to develop a CN-MCI-AD classifier that can perform better than existing methods. From our proposed approach of identifying features that are important for the classifier and recursively removing the less important features, we are able to achieve state-of-the-art accuracies as shown in the table here. Also, salient parts of the brain were identified based on the importance scores. We found 2 regions in the uncus and anterior extremity of the parahippocampal gyrus to be extremely relevant. Let's now go into the details of how these results were achieved. Several work has been done in this area of building classifiers for CN, MCI, and AD classification. In the past, support vector machines, or SVM, has been giving the highest accuracies. However, in recent years, there have been also been increasing interest in using neural network-based approaches, which in occasion outperform support vector machines. For instance, Mazzoleni et al. Proposed the use of a connectome convolutional neural network. Although neural networks are powerful, they are not easy to use with fMRI data. Most studies use a complete set of features as input, even though functional MRI datasets are often small, about 1,000 scans, and using too many features, like 30,000 features, will cause a model to overfit easily. Often, careful regularization has to be done, but model tuning is a laborious and time-consuming process. Furthermore, neural network models that have been proposed in recent years are increasingly complex. For example, there are models like deep autoencoders and Mazzoleni's connectome convolutional neural network, which has customized filters to fit connectome-based datasets. Even though these models might have been shown to give better results, there is no easy way to derive salient features from the model. Their sole utility is in performing the classification task. However, model interpretability is very important in the healthcare domain, and healthcare practitioners are often resistant to black box models. Thus, it is proposed that all we need is just a simple multi-layer perceptron used in an appropriate way to give state-of-the-art results. This can be done by identifying and removing the least important input features. This process can be done recursively until the model accuracy starts to decrease significantly from the model that's best performing. How do we assign important scores to the input features? To do so, we will use a method called deep lift. In general, the idea is to find the contribution of each node in the output layer and backpropagate the contributions of all the layers at the input layer. Deep lift propagates the difference in the output of samples from some reference output across different layers in the neural network. After experimenting with several approaches, it was found that the mean reference gave the best results. Our proposed method can be summed up into 5 main steps. First, we use 5-fold cross-validation to find the optimal set of model parameters for the initial model. Second, we use deep lift to calculate the importance score for all input features. Third, we remove 10% of the least important features, as ranked by deep lift. Fourth, the present neural network model will have its number of nodes in each hidden layer reduced proportionally, rounded to the nearest integer. Finally, the smaller set of important features is then used to train and test on a new and smaller model with appropriate train-test splits. Once this is done, we repeat from step 2 until the model test accuracy becomes significantly lower than the current best model. Having explained our proposed methodology, we will next elaborate on how the experiments were conducted. In analyzing data produced from neuroimaging techniques, there is an important distinction between the various modes of brain connectivity: structural, functional, and effective connectivity. Structural, or anatomical connectivity, refers to the physical connections that exist in the brain structure, i.e. whether one region of the brain is directly connected to the other. Functional connectivity shows the correlation between the regions of interest, while effective connectivity is concerned with the route of information flow, i.e. the causality between regions. In this project, we will be focusing on functional connectivity in resting state functional fMRI datasets. At present, ADNI provides one of the largest datasets available for researchers working on AD and its prodromal stages. As a long-term project, it has multiple phases including ADNI-1, ADNI-GO, ADNI-2, and ADNI-3. The ADNI-2 dataset was chosen as it is the latest version with RS fMRI data available. As we know from the previous section that age has an impact on brain structure and functionality, care was taken to ensure that the subjects are within the same age group. The ADNI dataset is the largest publicly available fMRI dataset for AD and MCI. As the scans for all subjects came from the same scanner, this removes the common problem of variations due to the scans coming from different scanners. Furthermore, it ensures that the results presented in this report are reliable and reproducible. The raw ADNI dataset had to be processed before it can be used as input to the neural network. First, we converted the raw dataset into a BITS-compliant format. Second, we used fMRI prep and FreeShuffle to perform pre-processing steps, such as slice time correction, head motion correction, and resampling. Third, we used Powers Atlas to gain 264 regions of interest of the brain. Fourth, we calculated the mean time series of all voxels within a sphere of radius 2.5 mm of each ROI. Fifth, we calculated Pearson's correlation to derive the functional connectivity between the ROI and all the ages between the 264 ROIs, arriving at a 264 by 264 matrix for each dataset instance. Finally, we took the lower triangular of the correlation matrix, flattened it, and then used it as input for the neural network. With this experimental setup, we were able to obtain results that outperform almost all previous models in all three classifications: CN versus MCI, MCI versus AD, and CN versus AD. Here, CN and NC refers to the same thing. To obtain the standard deviation, each experiment was repeated 5 times. From the table, we can see that even when the model is trained on less than 25% of the original features, it is able to perform at a level better than the model that used all the features. Also, it is superior to the SVM methods too, which were previously identified to be the best performing model for fMRI data. This table shows the model parameters used for these optimal models. These features show the sensitivity scores of regions of the brain that are important in performing the classification of CN and MCI from the perspective of the various anatomical planes: axial, coronal, and sagittal. From the box plot, we can observe that the regions in the superior frontal gyrus, containing both the medial and lateral regions, and the temporal poles, to be highly relevant for CN versus MCI classification. Also, the parahippocampal gyrus is highlighted. This heat map provides another perspective of which regions are important. We can see that the UNCUS has the highest sensitivity scores. These figures show the sensitivity scores of the regions of the brain that are important in performing the classification of CN and AD from the perspective of the various anatomical planes. From the box plot, we can see a similar emphasis on the parahippocampal regions. Additionally, the medial temporal lobe regions, fusiform, lingual, and angular gyrus are also highly discriminating. We saw some of these features in CN versus MCI too. From the heat map of CN versus AD, we also observe that the UNCUS has the highest sensitivities. The regions that have a higher sensitivities here, but not in CN versus MCI, are regions such as the occipital gyrus, both superior, inferior, and also middle. In summary, this study has the following novel contributions. We uncovered salient brain connections and regions using a reference-based decoder and showed that pre-training a model on an empirically relevant subset of features produces higher accuracy. We reported accuracies of classification for CN versus MCI, MCI versus AD, and CN versus AD. Previous studies have typically performed classification only on a subset of this class. We achieved state-of-the-art accuracies with the deep neural network in comparison to previous studies which use functional connectivity features. This methodology can be applied to neuroimaging data across different imaging modalities and other neurological and neuropsychiatric disorders. Furthermore, knowledge of such characteristic features of a brain state can help narrow down the focus of clinicians and help design diagnostic systems with higher accuracy.